Okay, so far we've talked about three-phase power development and what happens to a three-phase motor once we apply three-phase voltage to it, how it reacts, okay? Now, we do know that there are 5 things that we want our motor control system to do. And that's where we're going to start talking about a little bit about control, okay? First of all, we've been over the first 4. Okay? We want it to be able to start and stop the motor. We want to be able to control the speed. We want to be able to jog the motor and reverse it. We've been over that, okay? Now, today I want to talk to you about how we protect the motor and the circuit and ultimately ourselves and the equipment too, okay? So, there are 4 components to a motor control circuit. First of all, there's the disconnect, then there's the short circuit protection devices, the controller, and then the overloads, okay? We're going to go into each one of these in a little bit more detail, but I want you to have a good understanding of what each one of them does and also what each one of them does not do. It's just as equally important, okay? So far we've got 3 phases of voltage coming across our conductors, and we're going to get it to our 3-phase motor, okay? Well, we got to put some other components in our system in order to make it a full working motor control system, okay? We're going to start with the disconnect, okay? Now, there are a ton of different manufacturers of 3-phase disconnects. There's Square D, which is what these 2 are, and I've got a demonstrator that's a Square D as well. Allen Bradley, ABB, Cutler Hammer, the list goes on and on. So there are a lot of them out there. I think Square D and AB, or Allen Bradley, are probably the most popular in the in North America, I should say. Okay, they dominate most of the market, particularly in the industry. However, this is the 3-phase disconnect symbol. Okay, you'll notice here that this little dotted vertical line, that means there is a mechanical linkage between each one of these knives in the disconnect. In this particular case, we'd have our power feeding in from the left, where if it were turned this way, we'd have our power feeding in from the top, but in this case, we're feeding from the left. Our knives are not bridging the gap between our conductors and the rest of our system. They are in the open or isolated mode, okay? So right now, at 3-phase voltage, it would be going nowhere. It'd stop right there because we don't have it bridged over the rest of our system, okay? And it's designed to do that. Now, what we've got here to draw it in our system, we would put our 3-phase disconnect right here to the far left, and that'd be because we want to protect everything downstream of the disconnect, okay, from our 3-phase incoming voltage, okay? So what does a disconnect do for us? It isolates the 3-phase voltage from everything downstream. That includes the motor, the controller, and any other motor circuit components that are in our system, okay? In this graphic that I've got right here, we've got 3-phase voltage L1, 2, and 3 coming into the top of our disconnect. Now, the power always comes into the top lugs. It can come into this in from the bottom, but it has to go and terminate to the top right there. Okay, so our hot wire can come from the top, or our hot conductors can come from the top or from the bottom, but they have to be terminated on the top. Okay, they've got lugs to tighten them down with. Okay, and then we have 3 knives that will open up and isolate this 3-phase power from here, everything down to our system, into our system, including the conduit, the motor, and everything else that we've got in our control system. Okay. It also protects individuals from being hurt through either electrocution or accidental motor starting, okay? We don't want either one of those to happen. And I've seen a lot of times they'll have the disconnect handle pulled, and someone will not lock it out or lock it from becoming de-energized or becoming re-energized. And what happens is someone will come along and say, this must be the reason my motor won't start. And they'll throw the disconnect up, maybe completely different from the system they're thinking about, but they'll throw that disconnect up, and somebody on the other end is going to get lit up or hurt. I've seen it happen before. So it's got a lockout device to help protect us, okay? Now, what this is not is an interruption device. In other words, this is not a start and stop switch. You do not start your 3-phase motor or stop it with the disconnect. It's simply to isolate the power. The only time that you really need to be opening and closing a live circuit with the motor running is in an emergency situation, okay? If you've got to have that thing shut down and you can't get to the start switch from a control room or something like that, you've got to shut down. You can do it that way, but you run a lot of risks there, one of them being hurt from arc flash. So we don't use the disconnect as a start-stop device, okay? And the reason being is because the knives that fall into the slots for the hot wires, they're not designed to withstand arcing, okay? And I got a little video to show you. But first, before I do that, I want to show you this 60 amp square D 3-phase disconnect, okay? We can open the door here, and our handle is down, okay? So we are de-energized. Basically, we'd have our 3 phases of voltage being terminated A, B, C right here. These, you strip the wire back and stick it in the lugs and tighten the lugs down. Now, there should be torque values that you need to observe when you're installing one of these or working with them. There's a specific torque value. You don't want to get these too loose, and you certainly don't want to get them too tight. There's a specific value that you tighten down your conductors with, and it'll stay tight for a long, long time, okay? I've seen guys over-tighten them. I've seen guys not put enough torque on them, wind up building a lot of resistance, and they will blow apart, okay? But anyway, they've got 3 knives, and hopefully you can see these, the 3 knives here. And these knives basically will fall into a slot, okay? The knives will be hot, and I mean the slot will be hot, and the knife will fall in there and make an electrical connection for all 3 phases. And once the knives are in the slots, the power will flow from here on out. Now this is a fusible disconnect in that it has 3 fuses on board. Sometimes you won't have that. The fuse block will be somewhere else right downstream from the disconnect. It'll be just a regular disconnect. But this is a fusible disconnect, and it has clips to hold 3 fuse cartridges for short circuit protection, and we're going to get into that a little bit later too. And then you got 3 lugs here that you'll tie your motor leads to, okay? And you run your wire out to your conductors out to your 3-phase motor. But again, this is for isolation purposes. Now, whenever you are engaging or disengaging a 3-phase disconnect, or any disconnect for that matter, you'll always want to stand to the right of it before you do that, okay? There's a reason, and I'm going to show you why in just a little while when we talk about short circuits, okay? But what can happen is you can accidentally have a short in between your phases, and it will blow the door off of this thing, and it can hurt you very badly. So whenever you, regardless of how safe you think it is, whenever you're energizing a disconnect, always stand to the right-hand side and get it out of your line of vision, okay? Should be wearing safety glasses, but safety glasses don't stand a chance in a head-on arc flash. So always stand to it and take your line of vision somewhere else, okay, out of the path before you energize that disconnect, okay? So that's a little demonstrated for right there. And as I stated earlier, the knives are not, they're not designed to be able to withstand a lot of arcing. When you've got a motor that's under load and you're not using the proper motor starting devices, okay, you're not using that, you got a motor under load, when you close that knife into that slot, okay, there's arcing that will go on. And those knives and those slots are not designed to handle that. They are simply there to isolate it and keep it from your source to your downstream devices, okay? So here's a demonstration. As these pieces come together, this is slow motion. This is what the arcing will look like. Okay? So that was slow motion just to give you an idea of what the arcing takes place. And technically, that equipment there is not designed for that arcing either. They were opening and closing it under a load. So a couple more things about the disconnect before we move on. They need to be rated at 150% of your motor's full load amperage. Okay, so we know that from your previous reading that the full load amperage FLA is somewhere on your data tag or data plate on the side of the motor, okay? So it needs to be rated at 115. You simply take your full load amperage, multiply it times 1.15, because your 115% needs to be rated at least that much, okay? And it also needs to accommodate a means of locking the handle out. Again, I've seen people energize disconnects on people that are working downstream, and people have gotten hurt before. So it's imperative that they have a lockout mechanism on there, on the handle, okay? Now, that's the disconnect. Now I want to talk about shorts in our circuit. There's two types. There are phase-to-phase, is one type of short circuit, and the other type is the phase-to-ground, okay? So we're going to start talking about phase-to-phase first. What is a phase-to-phase? Well, using our graphic here, anytime you have L1 or L2 or L2 or L3 or any combination of these come in contact with each other, that is a phase-to-phase short. In the real world, how it happens is that there is always vibration around equipment and machinery, okay, in production particularly. But you'll wind up with conductors laying on one another, and particularly in a piece of conduit, and they will rub until the point where the insulation is rubbed bare on both of the conductors, and then all you've got is bare copper conductors touching each other, and that's where your short occurs, okay? And if we didn't have short circuit protection, things they would start to glow red hot and catch a lot of things on fire and damage a lot of things, okay? But again, a phase-to-phase short is any time two of the three conductors come in contact with each other. It could be all three come in contact with each other. That too is a phase-to-phase short, okay? Here's a small illustration here. You should know what this is a connection point. You should know what that is when we start to do some designing on systems. Okay, but all three phases should be theoretically going to the motor. The motor is our load. It's what resists our current flow, okay? And it turns that current flow into work, some form of work, in the case of conversely mechanical energy, where our rotor starts to turn, okay? But if you give the current a chance to opt out of that, it's going to take the path of least resistance, okay? So here you've got a wire drawn, a conductor drawn between two phases. So this is a phase-to-phase short, okay? And now, to give you some idea of what we're talking about, what kind of current is involved whenever we get a phase-to-phase short. Let's use our Ohm's law. You should know this. Volts times current times volts is equal to current times resistance, okay? So I've got a 480 volt motor, and I'm pulling 10 amps because I've got a 48 ohm motor, okay? I'm just using some hypothetical values just for this mathematical demonstration. Okay, well, if I have a short, a phase-to-phase short, where I basically eliminated my motor, remember the current is going to take the path of least resistance. It's not going to try to go through all the windings. It wants the path of least resistance, and that's this piece of wire right here. Okay, so if we take this, and now the current is ignoring the motor, and it's going from phase to phase. Well, we've got basically a ½ an ohm in our piece of wire, okay, in our conductor. Okay, it's a whole lot less than 48 ohms of resistance. So if we've just got the ½ ohm of resistance of that piece of wire here, well, if we get 480 volts divided by 0.5, you'll get the current draw in a phase-to-phase short. Okay, that's 960 amps. It's almost 1,000 amps. That's a ton of current. It's very dangerous, okay? So we've got to have short circuit protection devices to take care of surges such as that, okay? We can handle 48 just fine, but when it hits 960 because of a phase-to-phase short, we've got to have something to take our voltage out and protect everything downstream, okay? So this is a phase-to-phase arc demonstration. What they've done, they've built this mock-up of three-phase voltage coming in, and then they energize it. And what they've done is they have looped a small piece of wire from A phase to B phase to C phase, and they've tied all three of these together. And this also goes back to what I was telling you as far as the disconnect. When you need to be standing to the right of the disconnect before you energize it, and your line of sight is somewhere else besides that. It's off, hopefully in a perpendicular pattern, okay? But what they're going to do is energize this, and you're going to see the effects of a phase-to-phase short that doesn't have short circuit protection device, okay? Here's your three phases, and they're going to energize it.
Here we go.
That's why you don't stand beside in front of a disconnect. And they're going to do the same thing at about 75% speed. And again, that is why you don't stand beside the disconnect when you energize it. You never know when someone has wired this up and gotten some conductors, stray conductors crossing over between your two phases. It's happened. I've seen it happen before, and it would blow the door off. And fortunately, no one was hurt at the time I saw that, but it was certainly an eye opener. So that's why we do that. Okay. And then we also have the phase to ground shorts. That's just basically one of your conductors has rubbed and found its way to ground. Okay, the insulation has come off and it's found its way to the ground. Okay, it can be any of the three phases. This is the symbol for a ground. Okay, you should know this now. Okay, and our motor should always be grounded. In fact, every component of our system should be grounded in some way or fashion. Okay, we take our ground to earth ground and put our motor on there. That way, and I've seen this happen the most right inside this junction box on the motor, where a lot of times if the motor is vibrating, seal tight or the conduit itself will break as a result of it just being worked and worked and worked, finally it'll break. Well, what you have then is conductors resting on the edge of a metal knockout hole, okay? And that vibration will eventually abrade the insulation, and you got bare copper coming in contact now with this metal frame. Now, the frame should be grounded, okay? When you open up this junction box, you should see a green wire that's coming over from here, okay? This is your ground over here. Should be coming over here, and that will take care of any stray voltage that comes in contact with the frame. This is why grounding is so important. If you don't have the ground, okay, the conductor could abrade itself and come in contact with that motor. And if that motor is not grounded, then the motor will still run, and it's live, okay? It's hot, it's electrically hot. So if I go up and touch that ungrounded motor, I become the ground, okay? And all of that current will run through me, okay? Probably kill me. So that's why when you see conductors, ground conduction, they're not just an afterthought or something nice to have. They're absolutely necessary. They're necessary inside our disconnect. That's why we have a conductor, a grounding conductor, that stays intact at all times. When we pull the disconnect, we disconnect or isolate the three phases, but we never open up the grounding conductor. It's always intact. You'll also find, it's not shown in this illustration, but you'll find the actual box itself is grounded, because if you had one of these conductors get loose and actually touch the side of the box and it were not grounded, I go up to touch the box to open it, and that box is hot, I become the ground, and I'm lit up like popcorn, okay? So we don't want to do that. We want to make sure the grounds are in place, okay? So when we have shorts, whether they're phase to phase or phase to ground, we have virtually no resistance and we have excessively high current, okay? So how do we protect ourselves and our system from phase to phase and phase to short circuit conditions, all right? First of all, a short circuit protection device is designed to protect the people, the conductors, and the control devices and anything else downstream in the event that two phases short together, or if they have a phase to ground, okay? Our short circuit protection device has to open up immediately, okay? We don't want that 960 amps that we did in our math equation hanging around. Again, the wires will turn red hot and glow smoke, and we're going to have a fire or somebody's going to get hurt really bad, okay? So we've got to have our short circuit protection devices open instantly, okay? And we're going to talk about this too. If we don't have a separate overload, then we need to have our short circuit protection device be able to ride out the inrush current that a motor experiences when it first starts up. We'll be talking about that in just a second, okay? But one of the short circuit protection devices that we're going to talk about is a fuse. This is the fuse symbol, okay? Fuses, here's a couple demonstrations, or a couple illustrations, excuse me. This is a TRS type fuse. This is one with blades on it. It's all types of applications, different way they install them. Okay. This one here actually has a blown indicator. In other words, if the fuse were to blow, there's a little neon light there, well not neon, but a LED light that will light up and give you a visual indication, hey, this fuse is blown. Okay. Fuses are non-resettable. That's sort of the bad thing. Okay, they're non-resettable. when they blow, they're one and done. You got to take them, pitch them, go to the stores, and check them out and get some of the fuses and put them in. Okay, they are less expensive than circuit breakers, but again, you have to replace them over time. That could get more expensive than circuit breakers. And again, some of them have visually blown indicators. Now, one thing about fuses I want to talk to you about, particularly with these visuals, trust nothing, trust no one. Okay, always use your meter to determine whether or not a fuse is good or bad. First of all, isolate your power. You can first of all check the fuses hot. Okay, you can check this fuse is hot, and you've done that in lab before if you took 1002. But then once you suspect you've got one of the fuses bad, isolate the power with your disconnect. Shut it off, okay? Keep three-phase away from the fuses and on downward, okay? Still being very careful when you go inside the disconnect. You'll want to check the fuses outside, take them out and check them and make sure that they are actually bad, okay? And then put it back in. One other thing too is that if you have a blown fuse and you repeatedly are having to change these fuses, you've got a problem, okay? Don't work around it. One of the things you don't want to do is, I've seen this happen too, guys will come in there and they will take a fuse, they'll have to replace the fuse 2 or 3 times, they'll go get a bigger amp fuse, a higher rated amp fuse, and pop it in there, problem solved. No, what you've done is you've made the fuse, which should be your weak link in the system, you've moved that somewhere else. Now probably your motor's your weak link. And I guarantee you a motor's a lot more expensive than a fuse, okay? So don't work around the problem by changing to a higher amp rated fuse, okay? So fuses come in a couple different styles. There is the non-time delay. That'll hold about 5 times its rated capacity, or its amperage rating, for about 1/4 of a second. So we've got a 10 amp circuit, a 10 amp fuse that's non-time delay, okay? It will blow instantly. It can handle up to 5 times for about 1/4 second, which is almost instantly, okay? So we also have the time delay. These are designed to ride out the inrush current that I'm going to be talking about here in just a second. I'll talk some more about it. But it will typically hold 5 times its current value for about 10 seconds. Gives that motor a chance to start turning before it tries to, while it experiences a high current, before it tries to take the system out, okay? Here's what we're talking about for inrush current too, and you're going to get into this in lab. But the moment that we apply voltage to the windings of our motor, you get that rotating magnetic field. The split second we apply that voltage, that magnetic field starts turning. But the rotor has not had a chance to turn yet. I mean, we're talking just a split second. So we've got applied voltage, and before the mass of the rotor can start to rotate. Okay. So when that happens, we basically got voltage applied and the rotor sitting still. And our current goes up extremely high because we're not cutting those lines of flux in the magnetic field to get that rotor to turn. So for a split second, we have a very high inrush current. Our current goes very high. But the moment that rotor starts to turn that first degree of rotation, our current starts to come down. And the faster it spools up, which you've seen motors, most of you have seen a lot of motors spool up very quickly, that current starts to come down very quickly too. It comes down in correspondence with the rotation of the rotor. Likewise, if we load a motor up, if we whatever we're turning starts to cause the rotor to start to want to slow down, our current will go up. But right now we just want to deal with the inrush current. Usually, inrush current is somewhere between 6 and 8, maybe even 10 times the full load amperage, okay? So that's one of the reasons we have a time delay. We want to give it time to ride out this inrush, okay? If we didn't have the time delay, then we would trip it at the full load amperage value of that fuse. So we want to give it a time to ride out. Again, this is a very, very short period of time. You see how fast the rotor picks up, takes off, and running at normal speed. But that's you have the non-time delay and the time delay. Okay. So the other type of circuit protection that we have, and again, circuit protection could be from phase to phase or phase to ground, is the circuit breaker. This is the circuit breaker symbol. All 3 phases. They're interconnected so that when I throw a circuit breaker handle, all 3 are isolated from the 3 phases of the voltage. Okay, come in a lot of different shape, size, and they again a ton of different manufacturers make circuit breakers. okay? Single pole, double pole. In our case, we would use 3-pole for 3-phase, okay? The nice thing about 3-phase, the circuit breakers is that they are resettable, okay? They are more expensive. They should be more expensive than fuses, I'm sorry. They're more expensive than fuses, but you know, they're resettable. Also, you can use a visual indicator. Usually, most of you have probably seen a circuit breaker tripped at home in your breaker panel. It'll trip about halfway. You can use that as a visual indicator to determine whether or not which one of them is tripped, okay? You have, like fuses, with the non-time delay, you have the instantaneous trip that will trip out immediately after it sees its rated current value being reached. So a short circuit would reach it very fast, it would trip it out, okay? That's for the short circuit, and it does not allow for ride-through, okay? So that's something you got to consider also. All right. So before we go on, I want to talk. We talked about the disconnect and the short circuit protection, okay, in our system. What I'm doing now is breaking up the lectures into a couple of different videos so that it doesn't take quite as long to upload, and also give you a little bit of break in between. But the next video that I want you to click on and open up and view is we're going to cover overload protections, which is very different from short circuit. We're going to get those two separated to make sure you have a good understanding about that. And we're also going to talk about a manual motor starter. We're going to actually start getting the motor to run for us with the manual motor starter. So for right now, I want you to wrap this up, and if you got any questions, come see me, and then start the next half of the lecture video, okay? Thank you.